Today we're going to derive the power rule. And the power rule is just an easy way of taking derivatives of a polynomial. We're going to find out by using the limit definition of a derivative. We have our function f of x is equal to a times x to the n, where a and n are going to be constants, and x is going to be our variable, indicated by our value inside of our f function. Now, in order to find f prime of x, we know f prime of x is also equal to the limit of h approaching 0, where we have f of x plus h minus f of x divided by h. And this was discussed in the previous video and how to use this within examples. Now, if our function is f of x is equal to a x to the n, let's use this generic function and try to solve for f prime of x. So when we have f prime of x, we're going to carry our limit down to our limit of h is approaching 0. Wherever x is within our function, we're going to replace it with x plus h. So here we're going to have a times x plus h to the n minus a x to the n divided by h. In order for us to actually solve for f prime of x, we need to evaluate this limit, and we need for some way to cancel out the h on the denominator so we don't ever divide by 0. So we can factor out our a's out in front. So I'm going to get rid of the f of x and just say equal to a times the limit of h going to 0. And we have these quantities, x plus h to the n minus x to the n divided by h. Now, here is where the interesting thing is with this x plus h to the n. Because expanding this is the key piece in order to solve for the power rule or deriving the specific f prime of x. And what this is saying, or what theorem we actually need, is actually known as the binomial theorem. So if we have x plus h to the first power, we know we just have x plus h. There's one possible orientation for x and one for h. If we have x plus h to the second power, if we expand it, we know we have x squared plus 2 times xh plus h squared. And this comes from the fact there's two different positions, and if we just alternate or the different combinations of x's and h's, we can say we have xx as a potential combination, xh, hx, and hh. And since these two things are the same, they correspond to the 2 in front of the xh. There's only one here, so it corresponds to the x squared, and there's only one here which corresponds to the h squared. The different number of combinations, which is derived from the binomial theorem. There will be a video later about the binomial theorem, but all you need to know for this specific derivation is that x plus h to the n power is going to be equal to x to the n. There's only one way to derive all of the n positions being x's, plus n times, or there's n different combinations of where we can have x in every single position except one, and have one h term in there. And we can add up all the potential different combinations until we achieve there's only one specific combination for all of the positions being h's. This is all we're really going to need for this specific expansion. So we plug in x plus h to the n, where we have this formula over here, now on the right. What we'll get is that we'll get a times the limit of h going to 0. We're going to substitute this quantity in blue. We have x to the n plus n, x to the n minus 1 times h, plus all the intermediate terms, plus h to the n. And now we have the previous minus x to the n left over, divided by h. So as we can see, and from prior examples that we have seen, we can cancel out our x to the n's in our numerator. We're going to be left with a times the limit of h going to 0. And now we have n times x to the n minus 1 times h to the first power, plus all the intermediate terms, plus h to the n, divided by h. And the one key piece here is that all of the intermediate terms will have powers of h squared and higher up until we get to h to the n power. And so we can divide everything out by h, and what we'll get here is we'll get a times the limit of h to the 0 of n x to the n minus 1, and there's no h's in that specific term, plus all of the terms that are left over will have powers higher than h to the first power. And this is important. This is a common notation you'll see in your math classes, and this notation will just generalize all of the terms that will have powers of h to the first power and higher all the way up to the n power, or higher than 1. And so, whenever we have h going to 0, anything that has h to the first power or higher will essentially just go to 0 when the limit is evaluated. And since there's no h term in the first term, we'll be left with a times n to the x to the n minus 1. And this is also just your derivative of your function from the beginning. And so the takeaway of this is if you have your function that is a polynomial, or if you have a constant, multiply your variable to a power of n, the derivative of it is just going to be a times the original exponent times your variable to the power of n minus 1. So your original exponent minus 1. And now you're multiplying that exponent from before. And this is what you see a lot of the times in your calculus classes, in your math classes, that this is just the generic power rule for polynomial functions. I hope you have learned something, and I hope you have learned how to derive the power rule by using the limit definition of a derivative. Please like this video, and please subscribe to my channel for more math and chemistry related content.